All right, today we're going to continue on with the idea of functions and working with functions. But today's ideas are, we are now going to mathematically do things with respect to fractions that we typically do with numbers. We, on our calculators, can add numbers, subtract numbers, multiply and divide numbers. We do that regularly in our calculator, and we regularly do that just our mathematical computations. But what we're going to go into today is we're going to take a look at the idea of functions, and with the idea of functions, we are going to combine these functions through these basic operations: addition, subtraction, multiplication, division. So if we take a look at two functions here, we have f of x equals 5x minus 1 and g of x equals 2x plus 3. Mathematically, we can write the addition of functions f of x, or f plus g of x. That is the addition of two functions. Okay? How we can expand this is, bless you, we can write this as f of x plus g of x. And it's not a very difficult concept to be able to do here. We'll do basically a lot of algebraic ideas that you have done already, but we're putting it into a function notation. So if I'm asked to add f of x plus g of x, well, f of x is equal to 5x minus 1. G of x is 2x plus 3. We are adding them together. Well, to add these together, what do you think we should do then, Isaac? Combine like terms. Yes, just algebraic operations that you typically do. I take the 5x plus the 2x and the negative 1 plus 3. And add them together, McLean. What do you get?
7x plus 2.
Once again, algebraic ideas that you've done, but now what we're doing is we're putting this into a function idea and looking at it as functions. Well, when we have f of x minus g of x, f of x minus g of x, we had to take a look at, while we're subtracting these two functions, this is where you have to watch out a little bit. We still have our 5x minus 1, but now we are subtracting off, and we have to deal with the entire quantity, 2x plus 3. Common mistake is not to do the entire quantity, 2x minus plus 3. Now we have to use our distributive property, distribute your negative through, combine your like terms. What do you come up with?
3x minus 4.
3x minus 4, that's correct. Well, if I'm multiplying f times g of x, okay, once again, this is going to be a solid dot here, so I'll mark down here. We have a solid dot here. We're going to go to an idea of a composition, which is going to be an open dot, but this is a solid dot. So this means multiplication. This is f of x times g of x. Well, if we write out f of x, which is our still 5x minus 1, and multiply it with the 2x plus 3, typically what we will see is we will see this without the multiplication symbol in there, and this is moved a little bit closer together. Now now we are multiplying two binomials. So how should we multiply the two binomials? Once again, algebraically, what do we have to do, Judah? Foil it. Yeah, we just foil this out. We go first, outer, inner, last. So go ahead, foil it. First, outer, inner, last. Check your age with somebody around you. Once again, there should be nothing here that oohs and ahs you mathematically, because all throughout your algebraic career, you have combined the like terms, you have FOILed things out, you come down to solutions. Lily, what do you come up with?
10x squared plus 13x minus 3.
10x squared minus 13x minus 3, or plus 13x. Questions? All right, division. Well, if we look at division, we have the 5x minus 1 divided by our 2x plus 3. Well, there's nothing that we can really divide out here. If I just had an x down there, I could maybe do a little bit of simplification. But if I have division here, I don't have much simplification to do. So that is an acceptable thing. But the thing that we have to watch out for here is we have created a fraction. And when we create the fraction, we have to worry about the denominator. What can we not have in our denominator?
0.
0. Yeah. So we have the 2x plus 3. This cannot equal the value of 0. Or 2x plus 3 cannot equal a value of 0. So if we take a look at this, we can subtract our 3 over, divide by 2. So x cannot equal negative 3/2. So if we look at a domain, our domain is x is a member of negative infinity to positive infinity, but x cannot equal the negative 3/2. And you have to note that. Okay, because you've created the fraction. Once you create that rational expression, okay, you have to note, do I have to worry about eliminating a domain? When you deal with the domain, it's the intersection of the two domains of the two functions. The intersections, which means, once again, the common values. When working with division, you must exclude the value that makes the denominator equal to 0. Where if we take a look at our initial two fractions, or two expressions, the 5x minus 1 and 2x plus 3, do we have any limitations to our domain? Sammy, do we have any limitations to our domain? No. Okay? We can have any real number from positive to negative infinity. We don't have to exclude anything because of radicals, logarithms, the rational expressions or denominators. So we don't have to eliminate anything. So if I take one that's from negative to positive infinity as my domain, the second one from negative to positive infinity as my domain, the intersection is the values that are common in both. Well, all real numbers are common in both. So my domains here are going to be all real numbers. Bless you. Well, if we take a look at my two fractions here, I have f of x plus g of x, or I have f of x is x square root of x minus 3, g of x is square root of x. So if I look at my values here, if I'm adding these together, we have the square root of x minus 3 plus the square root of x. Now the question is, do we or can we combine these two things together? Can we combine them together, the square root of x plus x minus 3? Can we put them all together underneath one radical? Okay, now we have to think back to radicals. When I have addition of two radicals, can I combine them together? Or when can I combine radicals together? let's go back and look at the idea, the property of radicals. If I have square root of a times b, this is the square root of a times square root of b, and this will go in both directions. So when I have multiplication here, I can bring these together or separate them. But if I have square root of a plus b, can I separate these two radicals into square root of a plus the square root of b? Are we allowed to do that? Well, take a look at that then. Some of you have a little bit of a raised eyebrow. If I have the square root of 12, let's make it 10. Let's make it 11, there we go. The square root of 11. We can write square root of 11 as 9 plus 2. Are we allowed to say this is square root of 9 plus the square root of 2? No, we can't. We are not allowed to do that. Okay? That's where our good buddy Francois Viette, he is the father of algebra. You have our good old buddy Pythagoras. He's not too much into algebra. They would come and maybe arrest you if you try to do that. So you don't want to do separation with respect to addition. But if I have square root of 9 times 2, we could separate that square root of 9 times square root of 2. We're okay with that to give us 3 square root of 2. We're okay with multiplication, but when we have addition, we cannot separate in addition and bring them back together in addition. Even though we are tempted to do that, we're not allowed to do that. Because this is what people will do, square root of x squared plus 9. Well, that's square root of x squared plus square root of 9, so that's x plus 3. Is that allowed? No, it's not. So if we take a look at our domain here, the domain for each one of these, if I look at x minus 3, square root of x minus 3. What would be our domain for the square root of x minus 3? What would be our domain for the square root of x? Okay, this is what we just talked about in the previous sections. Okay, we just had the quiz over. We look at the domain. What would be your domain for each one of these? Write down your domain for each one of these. You don't have to worry about interval notation. You can just use less than greater than at this point, because we'll bring it together. What would be our domain for square root of x minus 3? What would be your domain for square root of x? Once again, these are things that we just completed. And you can just use, once again, less than and greater than if you want to. What has to be true, and just think about what has to be true about values underneath the radical. Okay, how do we set up a domain when we have square root of x minus 3? How do we set up a domain for square root of x? Connor, what's the first one?
X is greater than or equal to 3.
X is greater than or equal to 3. Because x minus 3 has to be greater than or equal to value 0, so x has to be greater than or equal to 3. Second one, Brenna? Can they equal? Yeah. We have to be greater than or equal to 0. Well, if we quickly look at a number line here, we have 0 and we have 3. The first one's solid dot on 3 going to the right. Second one's solid dot on 0 going to the right. Okay, so we have 2 solid dots there. Good morning, Mr. McFerrin.
We're just learning about solid dots.
And you can wait for the University of Findlay.
Wait.
Please wait.
There you go.
chicken. So if we take a look at the intersection of the values that are common in both. Okay, the values that are common in both. Well, what values are common in both here? Lloyd, what values are common in both? 3 and up. Can we include 3? Yeah, we can include our 3 and going to the right. That would be our intersection of these two sets here. So my domain down here would be x is a member of 3 to positive infinity and beyond. And that domain would be true throughout because that's going to be my intersection. A lot of times I'll sit there and go, yeah, I look at the idea of intersections, but a lot of times what I will do as I go through these is I will look at my final solution and I'll judge from my final solution what my domain is going to be for my final solution. Let's just go to the back here. If I have a function f of x equals 2x plus 3, f of x equals 2x plus 3, I want you to find the function values at 3, -5, 7, h, and j. What would be your function values for 2x plus 3 at those given values from the domain? Go ahead, find your values, check your answer with somebody around you. Natalia, what's f at 3?
9.
How'd you get it?
Plugged it in.
What do you mean by plug? What'd you do when you plugged in? What'd you multiply and add?
Oh.
Correct. What do you have to do? How'd you get it?
Oh.
Mathematically, what'd you do?
Oh. Plug 3 in for x.
2 times 3 plus 3. Plug 3 in for x. To give us a value 9. F at -5, what do you get? McLean.
-7.
How'd you get it?
2 times -5 plus 3.
F at 7, what do we get for F at 7? Caden.
17.
How'd you get it?
2 times 7 plus 3.
And what'd you say it was?
17.
Okay, F at H. What do we have for F at H? Zoe, what'd you get F at H?
2h plus
2h plus 3. Do we combine them together anymore? London, what do you get for F at J?
2j plus 3.
2j plus 3. Okay, and what we are dealing with here is whatever's inside the parentheses, once again, we substitute in for x. Well, what if I had F at dog? Zach, what do you think we'd have?
2 dog.
2 dog plus 3, that's correct. We'd have 2 dog plus 3, because that's what's inside the parentheses. So whatever's inside the parentheses, we plugged in for x. Well, what we're going to look at now is what is called a composition. We can add, we can subtract, we can multiply, and we can divide functions. Those are basic operations that we do with respect to numbers. Add, subtract, multiply, divide. But functions also have what is called compositions. And when we deal with compositions, we have a symbol this circle should be a little bit more in the middle here. F circle g of x, which is evaluating our f function at our g function. So we can rewrite f circle g of x as f of g of x, or g circle f of x, which is g of f of x. So we evaluate one function, and the x value we substitute in for is the other function. Just like we substitute a dog in for x, well, we're going to substitute another function in for x. Well, the domain of f circle g of x consists of the numbers of x in the domain of g, for which g lies in the domain of f. A little confusing, okay? It spins you around the circle real quick, okay? In essence, what you have to do is look at your final solution, and with the final solution, you can write a domain with your final solution. So if we take a look at f of x, g of x, still the same functions, 2x plus 3, 5, 3x minus 5. We want to find f circle g at x. Well, we look at f circle g of x, but sometimes it's called fog of x. This is by definition f at g of x. Now, slow yourself down as you go through compositions until you get used to them. Don't try to do too many things at one time. Okay, rewrite it as a composition, then start making some substitutions. As always, in parentheses, work yourself inside out. So g of x is defined to us as 3x minus 5. So this is f at 3x minus 5. Okay, all I'm doing is I'm taking this g of x out of here and replacing it with f of x, or with g of x, which is 3x minus 5. Now this tells us to evaluate our f function at 3x minus 5. Just like as you giggled up here, we evaluated this a dog. Wherever I saw an x, I put in a dog. Wherever I saw a j, I put in or x, I put in a j. X, I put in an h. Well, wherever I see an x in my f function, I'm going to rewrite 3x minus 5. So in my f function, we have 2. Then we see an x here, 3x minus 5. And then plus 3. So we are taking this x out of here and removing it to Texas. And then we can now simplify. So go ahead and distribute out your 2 through your 3x minus 5. Add your 3. Remind your like terms. Gabe, what do you come up with?
6x minus 7.
6x minus 7. Okay, good. And if I look at my domain, do I have any restrictions with my domain? No radicals, no logs. Go ahead and find G circle f of x. Check your answer with somebody around you. You're going through the exact same process, but now you're substituting your f function into your g function.
Just infinitely do that.
Wax off.
Amber, what do you come up with?
I was just, I guess,
Six X what?
just into right here.
6x plus 4, we'll go with that. Okay, once again, if I take a look, I have no radicals, I have no fractions, I don't have any limits with my domain, so my domain is x a member of negative to positive infinity for both of these and beyond. Let's see here. Let's find f circle g of x and g circle f at x for both of these. And then write your domain. Check your answers with somebody around you.
Oh, that's better.
I did split it.
Nobody can have it. Oh, you can't have a baby. Yeah.
So if we look at the first one, we have to evaluate our f function at x plus 5, which is g of x. So in our f function, we're putting in x plus 5 where I see an x. Brandon, what do you come up with? Well, let's substitute x plus 5 into our f function for x. So this would be square root of, substitute x plus 5 in. So we have x plus 5 for our x. Then we have a minus 3 still there. So wherever I see an x, wherever we see an x, we're going to substitute in x plus 5, just like a dog. Okay? So I can substitute x plus 5 in for x, and simplify. What do you come up with? X plus 5 minus 3. Combine your like terms with 5 minus 3. X plus 2. So we have square root of x plus 2. So if I take a look at my domain here, this x plus 2 has to be greater than or equal to 0. So Maddie, what would be our domain on this one?
X is a number, -2 to +2.
Can we include -2?
Yes.
Yeah, so we have bracket -2 to positive infinity beyond. Second one, we have to find our g at f of x. So we're going to evaluate our g function at, or our g at square root of x minus 3. If I evaluate my g function at x minus 3, Gavin, what you got?
Square root x minus 3 and then plus 5 out of the square root.
There we go. So we're going to see an x, I'm going to put that in. Only thing we have to worry about here is the square root of x minus 3 has to be greater than or equal to 0. So, Zach, what's our domain?
X is a number of 3 and then positive infinity.
Alright, we can include our 3. We can do this through a chart also. F circle G at 2. Once again, by definition, this is F at G of 2. Work yourself inside out. So first off, inside is what is our G function at a value of 2. Well, if I look at my chart, this gives me my X values on top, my F function, my G function. My G function at 2 is what, Lily? 1. My G function at 2 is a value of 1. So this tells me to take my F function now at a value of 1. Which takes us to what, Judah? 2. So my F function of 1, I get 2. What would be G circle F at 2? Once again, find your F at 2 first. Then find your G at that value. Check your answer with somebody around you. Connor, what's my F at 2?
5.
5. F at 2 is the value of 5. So then I have to find G at 5, which takes me back to 2. What would be F plus what would be F plus G at 2? Well, by definition, if I have two functions being added, I can write this as F at 2 plus G at 2. Oh, what is F at 2? What is G at 2?
6.
6. F at 2 is 5, G at 2 is 1. 1 plus 5 is the value of 6. Very quickly, if we go back up here, if we take a look at our solutions for G circle F and F circle G, one last idea. They are not the same. Well, in mathematics addition property, if I add 5 plus 4, I get 9. If I turn that around, 4 plus 5, I still get a value of 9. If I multiply 4 times 5 and 5 times 4, I get the same solution, which is called what property? Anybody remember what property that is? Nobody remembers. Start with a C. COM.
I don't know.
Oh, huh?
Is it commutative property?
Commutative property. There we go. Very good. Winner, winner, chicken dinner. Commutative property. So we can add and multiply, and that's commutative. But compositions, We could do that with also with functions. We can add and multiply functions and get the exact same thing. So our commutative property is still true. But when we deal with compositions, F circle G is not going to be the same necessarily as G circle F. Okay, so composition is not commutative. Compositions are not commutative in regards to operations. All right? Worksheet has a bunch of function operations here. Add, subtract, multiply, divide, but then you have compositions also. All right, questions you have? QED, as done.
Took 8 seconds to get out of the class. I know I can get out of it right now.